In the deepest darkness of the universe, far beyond the reach of ordinary starlight, something pulses with unwavering precision. A signal repeats again and again, not randomly, not chaotically, but with a rhythm so exact it rivals the finest clocks ever built by humanity. These signals do not come from planets, nor from galaxies, nor from any artificial source. They come from the remnants of dead stars, objects so dense, so extreme, that they bend the very rules of matter and time. These objects are called pulsars, and they're the cosmic lighthouses of the universe. To understand pulsars, we must first journey to the violent death of massive stars. When a star many times larger than our sun reaches the end of its life, it no longer has enough nuclear fuel to resist its own gravity. The core collapses in a fraction of a second, triggering a supernova explosion that can briefly outshine an entire galaxy. What remains after this cosmic catastrophe is not always a black hole. Sometimes the collapse halts at an extraordinary state of matter, a neutron star, one of the densest objects known to exist. A neutron star packs more mass than the sun into a sphere barely 20 kilometers across. Its gravity is so immense that atoms are crushed beyond recognition, forcing electrons and protons to merge into neutrons. The surface becomes a solid lattice of nuclear matter, and the interior may contain exotic states of physics that scientists can only theorize about. Time slows near its surface. Space curves sharply. This is no ordinary object. It is a natural laboratory for the most extreme laws of the universe. Yet not all neutron stars are pulsars. A pulsar is born when three crucial conditions align: rapid rotation, an intense magnetic field, and a misalignment between the star's rotation axis and its magnetic axis. This misalignment is key. It causes powerful beams of radiation to be emitted from the magnetic poles, sweeping across space as the star spins. When one of these beams crosses Earth, we detect it as a pulse of energy, brief, sharp, and astonishingly regular. The first pulsars were discovered in 1967 by Jocelyn Bell Burnell, who noticed mysterious radio signals that repeated with clock-like precision. At first, scientists were stunned. The signals were so regular that they jokingly labeled them LGM for little green men, suspecting an artificial origin. But soon, the true explanation emerged. These were rapidly spinning neutron stars, broadcasting their presence across the cosmos. Some pulsars rotate once every second. Others, known as millisecond pulsars, spin hundreds of times per second, faster than a kitchen blender, faster than anything human engineering could survive. Despite this speed, their rotation remains incredibly stable over millions of years. Each pulse arrives on time, unwavering, persistent, as if the universe itself were keeping time. The radiation emitted by pulsars spans the electromagnetic spectrum. Many are detected in radio waves, invisible to human eyes but clear to sensitive telescopes. Others shine in X-rays or gamma rays, releasing immense energy from regions no larger than a city. Near the pulsar's surface, particles are accelerated to nearly the speed of light, spiraling along magnetic field lines and generating intense beams of radiation that slice through space. These beams do not illuminate the universe like a star. Instead, they sweep through darkness, briefly touching distant worlds before moving on. Most pulsars are never seen from Earth because their beams never cross our line of sight. But for those that do, the effect is unmistakable, a cosmic heartbeat echoing across thousands or even millions of light years. Pulsars are not merely curiosities. They are powerful tools for science. Their precise timing allows astronomers to test fundamental theories of physics under conditions impossible to recreate on Earth. By observing how pulsar signals bend near massive objects, scientists confirm predictions made by Einstein's theory of general relativity. In binary systems where pulsars orbit other stars or even other neutron stars, their motion reveals subtle distortions in space-time itself. Some pulsars exist in pairs, locked in gravitational dances of extraordinary intensity. As they orbit each other, they lose energy by emitting gravitational waves, ripples in space-time that propagate across the universe. Long before gravitational waves were directly detected on Earth, pulsars provided indirect proof of their existence, validating one of the most profound predictions of modern physics. Other pulsars act as cosmic probes, mapping the invisible material between stars. As their signals travel through interstellar space, they are subtly distorted by clouds of gas and plasma. By analyzing these distortions, astronomers can reconstruct the structure of the galaxy itself, revealing regions otherwise hidden from view. In a universe filled with chaos, exploding stars, colliding galaxies, and turbulent cosmic storms, pulsars stand out as symbols of precision and order. Born in violence, they emerge as beacons of stability, marking the passage of time with relentless accuracy. Each pulse is a reminder that even in destruction, the universe can create something astonishingly elegant. And yet, pulsars are only beginning to reveal their secrets. Beyond their steady rhythms lie mysteries about the nature of matter, the limits of gravity, and the ultimate fate of stars. To follow their story further, we must venture deeper, into magnetars with fields strong enough to tear atoms apart, into pulsar winds that sculpt glowing nebulae, and into the possibility that pulsars may one day guide spacecraft through interstellar space like cosmic navigation beacons. The lighthouse has been lit, and its signal is calling us onward. As we move closer to these spinning remnants of dead stars, the true violence of their nature begins to reveal itself. A pulsar may appear calm in its steady rhythm, but surrounding it is an environment more hostile than almost any other place in the universe. The magnetic fields of pulsars are among the strongest known, trillions of times more powerful than Earth's. These fields dominate everything nearby, ripping atoms apart and forcing matter into shapes that defy everyday intuition. Near a pulsar, magnetic field lines twist and snap through space like invisible steel cables. Charged particles are trapped along these lines, whipped around at velocities approaching the speed of light. As they accelerate, they emit radiation in narrow, focused beams that cut through the cosmos. This process turns pulsars into natural particle accelerators, far more powerful than anything humans have constructed on Earth. Some pulsars take this extremity even further. These are known as magnetars, neutron stars with magnetic fields so intense that they can distort electron clouds and fracture the solid crust of the star itself. When a magnetar's crust cracks, it releases an enormous burst of energy, sending powerful gamma ray flares across the galaxy. If such a burst were to occur close to Earth, it could disrupt satellites and communication systems, despite originating thousands of light years away. Around many pulsars, a strange and beautiful structure forms, a pulsar wind nebula. As the pulsar spins, it ejects a continuous stream of energetic particles into surrounding space. When these particles collide with nearby gas and dust, they create glowing clouds of radiation, shining brightly in X-rays and visible light. One of the most famous examples is the Crab Nebula, the remnant of a supernova observed by astronomers nearly 1,000 years ago. At its center, a pulsar spins relentlessly, powering the nebula like a cosmic engine. These nebulae are not static. They ripple, twist, and evolve over time, shaped by the pulsar's rotation and magnetic field. Shock waves race outward at incredible speeds, sculpting filaments and arcs of glowing material. In these environments, matter behaves in ways that challenge existing theories, pushing scientists to refine their understanding of plasma physics and high-energy astrophysics. Pulsars also exist in systems where gravity plays a dramatic role. In binary systems, a pulsar may orbit a companion star, pulling material from it with overwhelming gravitational force. As this stolen matter spirals inward, it forms a blazing disk around the pulsar, heating up and emitting intense X-rays. The infalling matter transfers angular momentum to the pulsar, spinning it up to extraordinary speeds. These recycled pulsars become millisecond pulsars, some of the fastest spinning objects in the universe. Millisecond pulsars are marvels of stability. After being spun up, their rotation becomes so consistent that their pulses can be predicted years in advance with astonishing accuracy. This precision has turned them into some of the most reliable timekeepers known, surpassing even atomic clocks over long periods. In a universe governed by uncertainty, pulsars provide a rare sense of order. Because of this reliability, pulsars have become invaluable tools for exploring space and time. By tracking the arrival times of pulses from multiple pulsars spread across the sky, scientists can detect subtle distortions in space-time caused by passing gravitational waves. These waves, produced by supermassive black holes merging in distant galaxies, stretch and compress space itself. Pulsars act as a galactic-scale detector, silently recording these cosmic tremors. Pulsars may also play a role in the future of space exploration. Researchers have proposed using them as natural navigation beacons, allowing spacecraft to determine their position in deep space without relying on Earth-based signals. By measuring the timing of pulses from known pulsars, a spacecraft could triangulate its location anywhere in the galaxy. In this way, the remnants of dead stars may one day guide living explorers between the stars. Despite decades of observation, pulsars continue to surprise scientists. Some suddenly change their rotation speed in events known as glitches, likely caused by shifts within their ultradense interiors. These glitches offer rare glimpses into the structure of matter under extreme pressure, hinting at superfluid cores and exotic quantum states that cannot exist under normal conditions. Other pulsars display irregular behavior, switching their emissions on and off or altering their pulse patterns without warning. These changes suggest complex interactions between the star's magnetic field, crust, and plasma environment. Each anomaly challenges existing models and reminds researchers that pulsars are not fully understood machines, but dynamic, evolving objects. As we listen to their signals, we're not merely observing distant stars. We're hearing the echoes of cosmic catastrophe transformed into precision and light. Pulsars embody a paradox of the universe. From violent destruction emerges remarkable stability. From chaos arises rhythm. They stand as monuments to the extremes of nature, broadcasting their existence across vast gulfs of space and time. Yet there is more to their story still. Beyond their physical properties lies a deeper question about what pulsars reveal regarding the universe itself, about time, gravity, and humanity's place in a cosmos governed by forces far greater than anything on Earth. To explore that meaning, we must step back and consider pulsars not just as objects, but as messengers, silent narrators of the universe's most profound truths. When scientists first realized what pulsars truly were, the discovery reshaped humanity's understanding of the universe. These objects were not just remnants of stellar death. They were timekeepers, messengers, and witnesses to cosmic history. Each pulse carries with it a story that began long before Earth existed, a story written in gravity, radiation, and extreme physics. Pulsars challenge our perception of time itself. Their signals travel across vast cosmic distances, sometimes for millions of years, before reaching our instruments. When we detect a pulse, we are not observing the pulsar as it is now, but as it was in the distant past. In this way, pulsars act as time capsules, allowing us to peer backward into the evolution of our galaxy. The rhythm we observe today may have begun long before humanity ever looked up at the stars. This precision makes pulsars uniquely valuable to astronomers studying the structure of the Milky Way. As their signals pass through clouds of gas, dust, and plasma, they are slowed and scattered in subtle ways. By measuring these distortions, scientists can map the invisible material between stars, revealing the hidden architecture of the galaxy. Pulsars illuminate not with light, but with information. Some pulsars orbit black holes, forming systems where gravity reaches its most extreme expression. In these cosmic laboratories, space-time is warped to extraordinary degrees. The pulsar's pulses arrive slightly earlier or later, depending on how space-time bends around its massive companion. By studying these tiny variations, scientists test gravity in regimes far beyond what Earth-based experiments could ever achieve. Each observation strengthens or challenges our understanding of the universe's fundamental laws. Pulsars also offer insight into the nature of matter itself. Inside a neutron star, densities exceed anything found elsewhere in the universe outside black holes. Protons and neutrons are crushed together, possibly dissolving into exotic particles or forming superfluids that flow without friction. When pulsars glitch, suddenly changing their rotation speed, they provide rare clues about these hidden interiors. These brief irregularities are like seismic events, revealing the structure of an object we can never directly observe. Beyond science, pulsars have influenced the human imagination. Their regular pulses evoke the ticking of a cosmic clock, a reminder that the universe operates on scales far beyond human experience. They embody a strange blend of destruction and order, born from supernovae, yet enduring with remarkable stability. In a universe defined by impermanence, pulsars persist. Some scientists have even considered pulsars in the search for extraterrestrial intelligence. Their artificial-seeming regularity once sparked speculation about intelligent origins. While pulsars are now well understood as natural phenomena, their discovery reminds us of how easily the unfamiliar can appear intentional. The universe often creates patterns so precise they challenge our assumptions about randomness and design. As technology advances, pulsar research continues to expand. New radio telescopes scan the sky with unprecedented sensitivity, uncovering thousands of previously unknown pulsars. Some emit mysterious, fast radio bursts, intense flashes of energy lasting mere milliseconds, originating from distant galaxies. While not all fast radio bursts come from pulsars, certain highly magnetized neutron stars are now known to produce them, linking these fleeting signals to the most extreme magnetic environments in the cosmos. Pulsars may also shape the evolution of galaxies themselves. By injecting energy into their surroundings, they influence star formation and the behavior of interstellar matter. Their winds and radiation can compress nearby gas clouds, triggering new generations of stars or disperse material, preventing stars from forming. In this way, pulsars participate in the ongoing cycle of cosmic creation and destruction. Looking toward the future, pulsars may help humanity navigate the stars. As spacecraft venture farther from Earth, traditional navigation methods become less reliable. Pulsar-based navigation systems could allow explorers to determine their position anywhere in the galaxy by reading the rhythms of these distant beacons. The same objects born from stellar death may one day guide humanity's expansion into interstellar space. Yet perhaps the greatest significance of pulsars lies not in their practical applications, but in what they teach us about the universe's character. They reveal that nature is capable of producing both unimaginable violence and astonishing precision. They show that even in the aftermath of destruction, order can emerge, persistent, reliable, and beautiful. As we listen to their signals, pulsars remind us that the universe is not silent. It speaks in pulses and waves, in rhythms that span eons. Each beat echoes across space, carrying the memory of a star that once burned brightly and now endures as a spinning core of extreme matter. And still, the story continues. New pulsars await discovery. New mysteries lie hidden in their signals. With each improvement in technology, we hear their voices more clearly, revealing deeper truths about space, time, and existence itself. To follow this journey to its conclusion, we must consider not just what pulsars are, but what they mean for humanity's understanding of the cosmos and our place within it. As our instruments grow more sensitive and our reach into space extends farther than ever before, Pulsars are revealing a universe far more dynamic and mysterious than once imagined. What were once thought to be simple rotating beacons are now understood as complex, evolving systems, objects capable of changing, erupting, and even falling silent without warning. Each new observation adds another layer to a story that is still unfolding. One of the greatest mysteries surrounding pulsars is how they are born with such extreme properties. The collapse of a massive star happens in a fraction of a second. Yet in that brief moment, magnetic fields intensify to unimaginable strengths, and rotation speeds accelerate beyond comprehension. The exact mechanisms behind this transformation are still debated. Computer simulations struggle to fully reproduce the conditions inside a collapsing stellar core, leaving scientists to piece together the process from fragments of observational evidence. Some pulsars appear to fade with time, their beams weakening as their rotation slows. Eventually, they may cross a threshold known as the death line, where they no longer emit detectable radiation. These silent neutron stars continue to exist, invisible and undetectable, drifting through the galaxy as cosmic ghosts. How many such remnants fill the Milky Way remains unknown, but estimates suggest there may be millions. Others, however, defy expectations. Certain pulsars suddenly reawaken after long periods of dormancy, their signals returning without clear explanation. These awakenings hint at hidden processes deep within the star, perhaps shifts in magnetic structure or changes in the flow of particles around the pulsar. Each revival challenges existing theories and reminds scientists that even decades after their discovery, pulsars refuse to be fully understood. The relationship between pulsars and fast radio bursts has added another layer of intrigue. Fast radio bursts are among the most energetic events ever detected, releasing in milliseconds as much energy as the sun emits in days. When astronomers traced some of these bursts to distant galaxies, and eventually to magnetars, it became clear that pulsars, or their more extreme cousins, could produce phenomena on truly cosmic scales. These brief flashes connect neutron stars to events visible across billions of light years. Pulsars also help astronomers probe the earliest history of the universe. By using networks of millisecond pulsars spread across the sky, scientists are effectively turning the galaxy into a giant observatory. Tiny deviations in pulse timing may reveal gravitational waves left over from the formation of supermassive black holes or even from the early moments after the Big Bang. In this sense, pulsars are not only messengers from dying stars, but also from the deepest epochs of cosmic time. Despite their scientific value, pulsars also evoke something deeply human. Their steady pulses resonate with our instinct to seek patterns and meaning in the universe. Long before modern science, humans used lighthouses to guide travelers through darkness and danger. Pulsars serve a similar role on a cosmic scale, marking invisible paths through the vast and unfamiliar ocean of space. There is a quiet poetry in their existence. Born from catastrophic explosions, pulsars persist as symbols of endurance. They remind us that destruction is not an end, but a transformation. In their relentless spinning, they carry the memory of stars that once illuminated the universe with warmth and light, now reduced to dense cores that shine in a different way. As humanity stands at the threshold of interstellar exploration, pulsars may become companions on that journey. Their rhythms could guide spacecraft across distances so vast that Earth becomes a distant point of light. Future explorers may navigate by listening to the heartbeat of the galaxy, trusting signals emitted by objects older than civilization itself. Yet even if humans never travel to the stars, pulsars will continue their silent vigil. Long after our species is gone, long after Earth itself has changed beyond recognition, these neutron stars will keep spinning, broadcasting their pulses into the darkness. They are reminders of the universe's vast timescales, where civilizations rise and fall in the blink of a cosmic eye. In studying pulsars, we confront both the limits of our knowledge and the boundless scope of discovery. Each pulse is a question as much as an answer, inviting us to look deeper, to listen more carefully, and to remain humble before the forces that shape the cosmos. The universe speaks in many voices, through light, through gravity, through time itself. Pulsars are among its most precise storytellers. Their signals cross the void, carrying lessons about matter, energy, and persistence. They teach us that even in the aftermath of stellar death, there can be rhythm, order, and meaning. As the final echoes of their pulses reach our instruments, we are reminded of a simple truth. The universe is alive with motion and memory. And somewhere, far beyond the edge of our sight, a neutron star continues to spin, marking time, illuminating darkness, and guiding our curiosity ever forward. As this journey draws toward its end, pulsars stand before us not merely as astronomical objects, but as storytellers of the universe's deepest truths. They are reminders that the cosmos is not only vast, but disciplined, that amid turbulence and destruction, nature can create systems of astonishing regularity. Each pulse is a note in a grand cosmic symphony, repeating across time with unwavering precision. From the moment a massive star collapses, its fate is sealed, yet its influence is far from over. In the birth of a pulsar, the universe compresses matter to its ultimate limits, forging an object where gravity, magnetism, and motion are locked in eternal tension. The star's former brilliance is gone, but in its place emerges something arguably more remarkable, a beacon that can outlive civilizations and outlast planets. Pulsars teach us patience. Their timescales dwarf human history, reminding us that the universe does not rush. Some have been spinning for millions of years, maintaining their rhythm long before Earth formed its first oceans. Others will continue spinning long after the sun exhausts its fuel. In their persistence, pulsars place humanity into perspective, not as insignificant, but as momentary observers of an ongoing cosmic process. They also teach humility. Despite our advanced theories and powerful telescopes, pulsars still surprise us. Their glitches, sudden flares, and mysterious emissions hint that our understanding remains incomplete. Each anomaly is a quiet invitation to learn more, to refine our models, and to accept that nature often holds answers beyond our current imagination. In many ways, pulsars bridge the gap between the abstract and the observable. Concepts like space-time curvature, relativistic motion, and quantum states of matter are no longer confined to equations on a page. They manifest physically in pulsars, measurable through the arrival of pulses at our detectors. These stars translate the language of the universe into signals we can record, analyze, and understand. There's also a human element in how pulsars are studied and explained. In observatories and classrooms, professors guide students through the mysteries of neutron stars, using chalkboards, simulations, and stories to convey ideas that stretch the limits of intuition. In quieter settings, elders and teachers speak of the universe with wisdom earned through years of learning, passing knowledge from one generation to the next. In this way, pulsars become more than scientific subjects. They become tools of education and inspiration. The image of a teacher pointing to the stars, explaining how a dead star can still speak across the cosmos, captures something essential about science itself. Knowledge is not static. It moves, evolves, and is shared, much like the pulses emitted by a neutron star. Each learner becomes a receiver, interpreting signals sent from both the universe and those who studied it before. Pulsars also invite reflection on navigation, both literal and philosophical. Just as ancient sailors relied on stars to cross unknown oceans, future explorers may rely on pulsars to traverse interstellar space. Their steady signals could guide spacecraft where no human has ever gone, turning stellar remnants into signposts for discovery. Symbolically, pulsars remind us that even in darkness, there are guides, patterns that can lead us forward if we learn how to read them. As our technology advances, New generations of telescopes will listen more deeply to the universe's pulse. They will detect fainter signals, uncover rarer objects, and perhaps reveal entirely new classes of neutron stars. Each discovery will add a new verse to the story, expanding our understanding of how stars live, die, and endure. Yet even if every equation were solved and every pulsar cataloged, their meaning would not be exhausted. There is wonder in simply knowing that somewhere in the galaxy, a star spins alone, unseen, its beams sweeping across empty space. Most of its pulses will never be detected. They will pass through darkness, unrecorded, unheard, yet no less real. This quiet persistence speaks to a universe that exists not for observation, but for its own unfolding. In listening to pulsars, we are reminded that science is an act of attention. It is about tuning ourselves to faint signals, separating meaning from noise, and recognizing patterns that reveal deeper truths. Pulsars reward this attention with consistency, with signals that endure long enough for us to notice, study, and learn. As this documentary closes, the image remains simple yet profound. A dense star, no larger than a city, spinning in silence, sending out pulses of light that travel farther than any human voice ever could. These pulses connect past to present, death to continuity, chaos to order. The universe does not speak in words. It speaks in light, in gravity, in rhythm. And among its clearest voices are pulsars, cosmic lighthouses, marking time in the endless dark, guiding our curiosity, and reminding us that even after a star dies, its story is far from over.